Well, thank you, Sally, for the introduction and for giving me the opportunity to speak today. It's great to be a part of the energy community here at Stanford, where we not only have engineers developing new energy technologies, but we also have people looking at the economics and the policy and sort of the whole picture that is needed to solve the energy problem. And a lot of what we wanted to do in this series was connect the economics with the technology. And today I want to show you the technologies that are in the pipeline and that a lot of people are excited about. So I'll start with the Department of Energy's sunshot goal, which is to have the cost of installing solar cells down to $1 per watt. And roughly, when you get to that level, the cost of getting electricity from solar cells would be about the same as getting it from a power plant that runs off of coal or natural gas. You know, the details depend on location and various things, but roughly that's about where you need to be. And when they set out to do this, the cost of installing was at several dollars per watt. And so the goal was about a factor of 3 to 4 reduction. When you break this down, the module itself will probably need to be about 50 cents per watt. The inverter that turns DC electricity into AC electricity will probably be about a dime per watt. And then the cost of installing it, getting the permitting, all of that stuff will need to be about 40 cents per watt. Now, in the last few years, the price, and I use that word carefully, the price of silicon has dropped to about 65 cents per watt. And a lot of people think that silicon is going to accomplish this goal and that perhaps we don't even need to do any more research. We can just let the big silicon companies keep doing what they're doing, and we're going to get to the sunshot goal. I personally don't hold that view because I don't think that the cost of silicon solar cells is at 65 cents per watt. I think it's probably more like 85 cents per watt. And to get the installation goal, you probably need a higher efficiency. If your panels are at 18 or 19%, the area you have to install is larger than if they're at 25% efficiency. And so if you look at the DOE report, it's not just these numbers. They also say that the efficiency will probably need to be up around 25%. And the world record for silicon is 25%, but that's one small cell, and some costly things were done to make it. And I don't think that the modules will get to 25%. And so that's why I think more innovation will be needed. I would like to do a one-slide review of just some of the key points from the excellent lecture that we heard last week. Anshu showed us that silicon is currently competitive only in favorable locations and with the current subsidies. And of course, the long-term goal is to have solar cells competitive even without the subsidies. Of course, it would be nice and fair if there was a carbon tax, and that would also help the solar cells out. One of the most interesting plots from the talk has 3 things on it. And this red line is the learning curve that Dick Swanson has shown in several lectures here at Stanford. And that was the cost reductions that you expect from efficiencies as you scale up manufacturing. And then in green, you see the sustainable cost, and this was found by looking through the statements of the companies, and you see that it actually fits the expected cost curve reasonably well. But then if you look at the price, you see the price dives much lower. And the price going lower, that extra bit here between cost and price, that has nothing to do with engineering or factories. That's economics 101. And people got too excited and built too many factories a few years ago. And right now we have a substantial oversupply. And so probably as the demand catches up with supply, the prices will actually, they might rise up faster than the costs will drop. And so I personally don't think we will see the costs at 50 cents per watt in a few years. Maybe something more like 65 cents per watt. Okay, so moving forward to the technologies and the various options we have. One of the things that makes working in solar cells so interesting is there are a huge number of ways to make them. Nearly everyone believes that the option that they work on is the best and will be the winner. And there are smart people who believe in all of these, and it really is not clear which one of these technologies is going to win over the long run. But the three broad classes of solutions are crystalline silicon, where you take wafers of, or you take big single crystals of silicon, and you slice wafers and build your PN junction. And then you have your thin films, where you use much less semiconductor, and usually you put it on glass, but it could be a metal foil, maybe even plastic. And then you have the Ferraris, the epitaxially grown multi-junction cells that have world record efficiencies, but they're extremely expensive. But you would use them with concentrators so that the area of the cells are very small. But one of the things you're going to see today is these boundaries are getting blurred because the silicon and gallium arsenide are starting to get very thin, such that you might call those thin films. And then we usually, although technically here you do have thin films, we don't usually categorize them as thin films, but you might see multi-junction made by low-cost processing, in which case it could be unclear which of these categories to throw them in. This is the famous NREL chart. NREL keeps track of all the world records. And I know you can't read it all, but the only point I want to make is that the efficiencies are rapidly rising for many families of materials. And one reason I just say this right now is it's always interesting to me to hear what people say, random people that I meet everywhere, when they find out that I work on solar. And so many people seem to think that it's a dying industry and things aren't going well. And this couldn't be further from the truth. The technology is getting rapidly better. Here you see the multi-junctions shooting up, gallium arsenide going up. Just last week, we saw a world record for cadmium telluride at 20.4%. The organic solar cells are rapidly getting better. Interestingly, the technology that completely dominates the market, silicon, has not had a world record in 16 years. So you can see that the Chinese went with old technology. They invested about $42 billion to push it forward and make it happen. Here in the United States, we've chosen to develop technologies that many people think have the potential to be much better, but we've been unwilling to invest as much, and we've not, gotten the factories up and working. But whether or not, what's going to win in the long run, I think remains unclear. Down here is a data point few people ever notice on the curve. This is the best tandem cell, where, or that's another word for a multi-junction cell, where the layers are polycrystalline and they're deposited at low cost. There's only one data point, but My group can now beat this, and I'll show you that later on. And a company called Styon just last week announced that they're at 23% efficiency. And I think this has been a highly unappreciated but very promising approach. So let me first just say a few things about silicon. It's really helpful, I think, to just take a simple look at what it is and then look at where the cost breakdowns are. So with this technology, you have far more silicon than you need. And really the main reason for that is just that you're slicing wafers. And right now it's very hard to slice thinner than about 150 microns. When you go thinner, you just have a lot of problems breaking the wafers. And it's not to say that it can't be done, it's just that's where things are right now. It's doped at the top to form a p-n junction. The higher performing cells don't have metal everywhere, they just have stripes of metal electrodes. And then the rest of the silicon is passivated, and that just means that you react the silicon with oxygen or nitrogen so that the dangling bonds don't cause recombination. You've got texturing up here that scatters the light and helps it get absorbed in here. So this is all pretty well developed technology going back to the 80s and 90s. What you see here is a cost analysis. This was done by Tonio Buonassisi at MIT. I think in renewable energy in general, we need to see a lot more of this kind of analysis. Any academic can come out and say that their new approach is going to fix all of the problems, and sometimes they can show high performance. But rarely do you see numbers as to what these things are actually going to cost. And Tonio did the hard work of talking to a lot of companies and finding out, what every single step costs and what all of the materials cost. And certainly don't have time to go through all of this. You can look the paper up and read it yourself. Another group, Mike Woodhouse at NREL, is doing very similar analysis. And the numbers from MIT and NREL are in nice agreement with each other. And what they think is that in 2012, for manufacturing in the US, the cost was, they had it actually at about $1.29 per watt, which again is why it was very hard for me to believe that the cost was really 65 cents per watt. And I just can't believe that China can do it at half the cost of what we can do here in the United States. And then 2020 here, LOS means line of sight. And that means that if you do a whole bunch of things that we're pretty sure can be done, then you can see how much you're going to drop the cost. And then out here, 2020, this is advanced concept. And this is where you have a very thin wafer and you have some way of generating it that does not require sawing through the wafer. And my opinion is these line of sight things are very likely to happen, almost a certainty. But when you take that next leap, it's not clear that we can get these super thin wafers and handle them in high volume without them breaking. And so I would say this is high risk. Like everything else I'm going to show you today. And nothing I'm going to show you today is a sure bet. They're all high risk but high reward approaches. If you read into this paper, you see all the costs, and some of them are going to be really hard to cut, but some of them look very promising. And so the silicon itself is very expensive. And if you can saw thinner, you can do a lot better. But if you can, radically change the game there and go from 150 microns all the way down to 10, this is where you can go from about 23 cents per watt on silicon down to a penny and a half. And then, of course, if you don't do wire sawing, then you can cut that to zero. Interestingly, another one that jumps out is the silver paste. And if you can find a way to use less paste or use a metal that's not as expensive as silver, there are opportunities for big improvements there. So just to show you that people are working hard on this, a company, SelectCell, that's nearby and affiliated with several professors at Stanford, including Krishna Saraswat. They're making great progress in getting the wafers thinner. And here they grow the silicon and then they lift it off of the wafer and they can reuse the wafer. And here you've got a 43 micron cell. You see that when semiconductors are thin, they also become flexible. And they've got a very respectable efficiency at 20%. In this slide, you see what the cells look like. And here they're set up as roofing shingles. And there's someone walking on them. And you can see that they're not breaking. And you also see that they look really nice. And I think that is the future of solar cells. Solar cells they should be absorbing all the light. And if they are, they're going to look black. And it is, as Dick Swanson has shown us, it is possible to put all the metal on the backside where no one can see it. And so I think in the future, solar will be very aesthetically pleasing. Yi Chui's group has done work in a new kind of light trapping. Conventionally, you etch pyramids into the silicon, but when you have a 10 micron thick wafer and you want to etch several micron thick pyramids into it, sometimes stress can cause the whole thing to curve. And so it could be better to have these nanocones that cause the refractive index to gradually change. And for that reason, the light doesn't reflect. And in this paper that will come out soon in Nature Communications, Sang-Moo Jiang showed that you can get essentially 100% light absorption in these 10 micron thick solar cells. But the real challenge is just going to be the manufacturing and figuring out how to do this at high volume and low cost. Okay, now I'll move on to the next exciting technology. There's been a resurgence of interest in gallium arsenide over the last few years. In some ways, it's the ideal semiconductor because it has a band gap of 1.4 electron volts. And that's the optimal gap for absorbing a good chunk of the solar spectrum, but still generating a high voltage. Perhaps the bad thing about it is that it only really works well if you have very large crystals and preferably a single crystal. And to grow these thin films of gallium arsenide, you need a single crystal substrate, and it needs to lattice match to the gallium arsenide. And then you need to grow the gallium arsenide slowly at high vacuum with a technique like MOCVD. And there's been a lot of cost in the single crystal substrates. They're way more expensive than silicon, and a lot of cost associated with the growth here. So Alta Devices has really changed the game with the wafer cost itself. And the idea here is that you grow your gallium arsenide on top of just a little bit of aluminum gallium arsenide. And you can etch aluminum gallium arsenide without etching gallium arsenide. And that means that you can take your solar cell off of the wafer. Now you have a very thin solar cell, and then you can polish the wafer and reuse it and potentially use it as many as 1,000 times. And so that greatly cuts down on the costs associated with having these single crystal substrates. However, you still have to grow the 3.5 semiconductor, and that itself can be expensive. One thing that's been really interesting to see in the last few years is that the approach also made the solar cells better. Not only were they cheaper, they actually work better than the solar cells where you leave the gallium arsenide on the substrate. And Eli Jablanovic has shown us that that's due to photon recycling. In gallium arsenide, non-radiative recombination is so rare that almost all recombination results in a photon being emitted. And that photon can simply be reabsorbed, regenerating the carriers. Now, if you have a thick wafer, the photon could go deep down into the wafer and generate carriers far away from the p-n junction. And then you might lose those carriers. But if you have a thin cell and a good mirror, then you can really keep those photons trapped up near the p-n junction, and you can just recycle those photons and put them to good use. And that resulted in the world record efficiency of, I believe, 28.8%, which is the record for a single junction solar cell. But this technology is still a very expensive one. And as I said earlier, I'm a big fan of rigorous cost analysis. And in this case, Mike Woodhouse and Alan Goodrich at NREL have talked to many people who are in the 3.5 industry. A lot of them make gallium nitride LEDs and have lots of data on making these kinds of devices at large scale. And they gave me about 30 slides of analysis. I'll only show you some highlights if anyone wants to see the details and all the assumptions that go into these calculations. I do have that information. And what they do is they come up with a process flow. They take into account every single step in the process, and they figure out what it's going to cost. And I'll just show you an example for one of the steps, which is one of the most critical steps. So this is the cost for the wafer itself as a function of how many times you're able to reuse the wafer. And they don't even start it at 1, they started at 5. If you could only reuse the wafer 5 times, the wafer's contribution to the cost of the cell would be $16 per watt. And let me remind you, our goal is 50 cents per watt for everything. And this is just for the substrate alone. With lots of reuses, you get that to $4 per watt. And then in their analysis, it saturates at $4 per watt because they think that's what it's going to cost just to repolish the wafer. And so that's about where you can get. Here's, now I skip all the way to the end of their analysis. I'm not going to show you a slide for every single one of these steps. But you see that the 3 big ones are the wafer. And then right here, this is the deposition of the gallium arsenide. That comes in at about $2.50 per watt. And then there's a gold electrode that comes in at about 30 cents per watt. So we see here making these cells is not as cheap as some people would lead you to believe. This is called a waterfall chart, and what these charts typically do is they tell you where we are today, where we think we could get with expected innovation, and then they tend to move towards dream scenarios. Sometimes when there's a 4th one on a waterfall chart, that's where miracles need to occur. And of course, the final is always going to be the sunshot goal. And you see that there would need to be some really big innovations to get down into that sub $1 per watt regime. And so I think in the short term, what you're going to see is Alta Devices is not going to try to compete head-to-head with silicon or fossil fuel power plants. You're probably going to see portable products, and this is off of their website. And if you built a case for an iPod, an iPad or a phone, you could get about 4.3 watts on a 7-inch tablet or 1.3 watts on a phone. When you plug a phone into the wall, you draw 8 watts, so it's within a factor of 4 just with the area that you have available on the phone itself. And what I hope happens is that this will keep the business going, allow them to start scaling up, and start realizing some of these cost benefits. And I hope they'll be able to go through several generations of technology, and that we will see them go down that waterfall chart. Because although it is too expensive today, I think it is an incredibly exciting technology. Not only are those cells highly efficient, they're also very thin and flexible. So, where could the breakthroughs come? Hopefully what the cost analysis does is not cause you to give up, but hopefully there's someone in the room who says, I can figure out how to make that deposition faster. One thing you can do is make the cells thinner, and Jim Harris gave a great talk at the GCEP meeting in October, and you can watch that talk on the internet. And he showed that with light trapping, similar to what I showed you earlier, you can make the gallium arsenide thinner, and then that's going to greatly cut down on your deposition time. And then another possibility is using concentrators. And when you use super expensive multi-junction cells, you're forced to use 500x concentrators. And when you concentrate that much, you need to point them right at the sun. Your trackers need to work extremely well. But since these cells are nowhere near as expensive, they're a little too expensive to use standalone, but only by a little bit. So, a 10x tracker would be perfectly acceptable. And you don't need, it's just much cheaper to make a 10x tracker. Okay, moving on to the next class of technologies, we have the thin films. And I'll just say a little bit about this. Thin films in the commercial sector have sort of taken a beating lately. A lot of the startups have gone out of business. But a lot of people who think thin films have lost the game do look over the fact that First Solar is doing extremely well. And they just announced a world record of 20.3% efficiency last week. And for many, many years, CAD/TEL was stuck at about 16%. And I know that at First Solar and at General Electric, they stepped back and they had some teams who did not focus on manufacturing. Instead, they went back to the basics and tried to have a deep understanding of what happens in these cells. And that appears to be paying off. And now the efficiencies are shooting up again. And I guess what I want to say about thin films is that, around 2005, people thought they were within striking distance of making it big. And the fundamental research kind of slacked off, and the companies went after scale up. And I guess they went a little too soon. Or maybe it shouldn't have been an either or. It would have been good if academics had continued to do this research, but largely they didn't. They went for higher risk approaches. And so a lot of the work that probably should have been done wasn't, but maybe it is getting done now. And we're back on an upward curve here. And who knows, CAD/TEL might be 23, 24, 25%. In a couple of years. This is some of the progress First Solar has made. Right now they're at 53 cents per watt, which is outstanding. And I do believe that number. I think the company simply does not have a source of income to sustain operating at a loss. And so I think that, that those are real cost numbers for them. And the modules now are at 13.4. They're obviously not yet incorporating the technology that was just announced last week. So you can certainly expect the efficiency there to rise and potentially compete with silicon in the coming years. But as I started with, we really do want 25% or higher. 30, 35 would be even better. And as many of you probably know, the fundamental problem we run into when we try to go over 30% efficiency is that when we excite carriers up into the gap, up into the conduction band, they rapidly relax to the bottom of the band and we lose that energy. And that makes us want to use a high band gap to avoid the thermalization losses. And if we do that, we can get a high voltage, but then we can't absorb the low energy photons. And there are a lot of so-called third generation approaches to solving this problem. But there's only one that works. The others are really not even that close to working, and in my opinion, don't have a plausible pathway to getting there. And so I'm going to focus on the multi-junction cells. This is a slide from our own Jim Harris, who has been making these cells, I think, for more than 20 years, although not continuously. And the idea is simple. You have high band gap, medium band gap, and low band gap cells. The light needs to go through the high gap cell first. You harvest the high energy photons, and that cell can generate a high voltage. And then the medium band gap cell grabs the middle of the spectrum and gives us an intermediate voltage. And the low gap cell takes most of what's left. And this works. It works great. Recently, some Stanford alumni had the world record at Solar Junction. Unfortunately, the Germans have taken it away from them and announced 44.7% efficiency. So I hope Solar Junction can rally and be the first ones to get to 45% efficiency. And here, we see a plausible pathway to 50% efficiency. I think we can expect that to happen in the coming decade. But this is a very expensive technology. This is a cross-section of a typical multi-junction cell. There's around 20 layers in here. Every single one of those layers serves a critical purpose. And this is all grown slowly. There's a single crystal substrate, and there are low defects all the way up through this structure. So you can really only utilize these cells right now with a high level of concentration, and then that requires the tracking. And it's still not clear that the costs of the concentrators and the trackers will come down enough, to hit those sunshot goals and be at 50 cents per watt. So what I'm a big proponent of is finding some way to build a tandem solar cell that does not require slow epitaxial growth of the second solar cell. And so my group is working on what we call a hybrid tandem. And the idea is that the bottom cell will probably be silicon or SIGs, because the bottom cell should have a band gap of 1.1 electron volts, and that's exactly the band gap of silicon. And also copper, indium, gallium selenide can give you that band gap. And I say silicon because practically, right now, more than 85% of the market is based on silicon. and huge factories are built in China. They've got great economies of scale, and I've learned the hard way that around here it's going to be awfully hard to form a startup and raise the capital you need to compete when they're at that scale. So if you can basically upgrade silicon by putting something on it, you're not proposing to shut down the factories that have been built. You're just proposing to add some tools into them and take silicon or SIGs from where it is up into the mid-20s for efficiency or even higher. And in a talk like this, I want to be open to many possibilities of what that top cell could be. The idea, if it's a thin film, is that it's something that is defect tolerant. So like an organic semiconductor doesn't need to be a single crystal. Soon I'll tell you about the new Perovskite materials. Maybe it could be a 2,6 semiconductor. One idea is that it could be a nanowire. And see here, if nanowires are small enough, they don't have to lattice match their substrate because you can't actually form a dislocation defect in a small nanowire. I used to think nanowire solar cells would never be very efficient because you get recombination at surfaces, and these devices have a lot of surface area. But it turns out that indium phosphide has a very low surface recombination velocity, 170 centimeters per second, which is more than 1,000 times lower than it is for silicon or gallium arsenide. I don't know if anyone understands why it's so low, but it is low. And it tells us that surface recombination is not necessarily something that has to kill a nanostructured device. And I'll show you later that there's a material that's even better than indium phosphide. And so these solar cells here are at 13.8% efficient. And who knows where the nanowire solar cells will go from there. There's one technology that pretty much all I know about it is stated on this slide here. Steion is not telling us much about how they made their tandem. I believe it has SIGs on the bottom with probably a lot more indium than gallium in the bottom cell. And then the top cell probably has very little indium and therefore a much larger band gap. It's probably a 4-terminal tandem, and they're saying that they are at 23.2% efficiency. So there's a company that also believes there are low-cost ways to make tandem solar cells. In the rest of my talk, I'm going to tell you about the newest kid on the block, Perovskites. They've taken the solar community by storm over the last 12 to 18 months, pretty much coming out of nowhere. And here's the crystal structure of this material. It's similar to barium titanate or the superconductors that a lot of people in the physics department like to study. You've got lead and then usually iodine, but you can also have bromine there. And then the ion that wasn't so obvious is methylammonium. I've talked to a lot of people over the last 10 years who wanted to do combinatorial approaches to screening potential solar materials. I've heard many elements discussed, but never anyone talking about putting an organic ion into the mix. And that turned out to be critical to get the right structure. Here you can see the efficiencies shoot up. Just 18 months, well, 24 months ago, they barely worked at all. There were only 2 papers. Then Snaith and Gratzel both announced 8%, and then just a half year later, they both announced 15%. And right now, I believe the record is at 15.9%. If you remember back from the NREL chart, Normally it takes over a decade to get a material over 15%, and it normally takes 100 people working for a decade to get there. And here teams of just 5 or 6 were able to break 15% with just a little bit over a year of work. So it's a very special material. Originally, it was used as a replacement for dyes in a dye-sensitized solar cell. You'd have a nanoporous film of titania, and then you'd fill it with the perovskite. And on the bottom, you'd have an electron withdrawing contact, and on the top, you'd have a hole withdrawing contact. This works well. You can get 15% efficiency. But Henry Snaith has shown us that you don't need the titania. You can just make a planar PIN junction. Here you do have titania, but not a porous film. You just have a solid film of titania that's N-type. Then you have undoped intrinsic perovskite, and then you have a P-type organic coal transporting layer. And this works very well too, with 15.4% efficiency. And so here you realize that this is really very similar to CIGS or cadmium telluride. It's a polycrystalline semiconductor where there's very little recombination, even though there are a lot of grain boundaries in there. The voltages are very high for a polycrystalline material. And a paper just came out showing that the defects in this material give you trap states that are very, very shallow. They're right at the band edges. And that's probably why this material is so special. States in the middle of the gap rapidly increase recombination, and they're real killers. Silicon and gallium arsenide have their traps there, and you're forced to use single crystals with those materials. But here, it's a very defect tolerant material, and that's probably why so many groups are getting high efficiencies so easily. It's also a great absorber. It absorbs light even better than gallium arsenide. So my group wants to make tandems, and for that we need about a 1.8 electron volt band gap. And Eva Unger, in collaboration with Hema Karunadasa's group, has varied the halogen content. By putting in bromine, we can gradually tune the band gap and get pretty much whatever band gap we want for a tandem solar cell. So then we've gone on and started making the tandems. We're considering both a 4-terminal architecture where we basically have 2 different solar cells, and the top one is transparent so that the low energy photons can go right through. In the short term, this is easier for us to make, but in the long term, we'll probably build it all on one substrate and match the currents of the 2 cells. We'll do that to get rid of these transparent electrodes, which can absorb some of the light. This cell was made by Colin Bailey and Gray Cristoforo, and just 2 hours ago they gave me better results than this. Last week, the best semi-transparent cells were 10.4%, and the special top electrode was made with a mesh of silver nanowires. These work really well, better than the conventional indium tin oxide, and we can put them down at low temperature without depositing our organic hole transporting material. Today, we have the semi-transparent cells at 11.6% efficiency. And we have SIG solar cells that Ramel Nufi gave us from NREL. And by itself, the SIGs is at 16.7%. And when we put the perovskite on top, of course, the SIGs goes down because a lot of the photons are absorbed in the perovskite. But our 4-terminal tandem is better than either solar cell by itself. We're now at 17%. And this is just the beginning. Gray and Colin give me better cells every week now, and there's a lot of easy things to fix here, and I think we'll go over 20 soon, and I think we have a plan to go to 25% efficiency. Just show a tiny bit here on the cost estimate to try to convince you that this is promising. Today, silicon is something like 19% efficient, $153 per meter squared, 79 cents per watt. Basically, what we're saying is if you give us another $14 per meter squared to deposit a few extra layers, then we think we can bump the efficiency up to 25%. Now your cost per watt drops, and your installation costs will go down because you won't need to put in as many panels. And then, of course, the silicon will get better. Silicon probably will go to 50 cents per watt someday, and then that means that the hybrid tandem might be something like 40 cents per watt at 25% efficiency. Okay, so I hope I've shown you some exciting technologies. I think right now conventional silicon clearly leads the race, but I don't think it's going to take us all the way to where we want to go and to hit those sunshot goals. But there are several technologies that could take over. It could still be silicon, just very thin silicon. It could be the gallium arsenide. It could be much better thin films, or it could be a hybrid. It could be perovskite on top of extremely thin silicon. I don't believe these technologies necessarily compete when you start putting them on top of each other in hybrid tandems. We're still discovering new materials. We're still getting surprises. I don't think a lot of people predicted that the indium phosphide nanowire solar cells would work as well as they do. The perovskites shocked everyone. We don't even know what the surface recombination velocity is because it's so low we have trouble measuring it. I can say it's less than 60 centimeters per second. Some might say, well, the lead perovskite is toxic, and that's true. But there's a whole new territory of materials that we can explore, and we might find less toxic and even better materials there. So there's still good basic research to do. And I believe someday we will have multi-junction solar cells that will be thin, they'll be light, flexible, and cheap, and over 30%. I really don't think it's going to be just plain old vanilla silicon dominating the market in 15 or 20 years. And just some more closing philosophical thoughts. It kind of bothers me when I hear people talk about sort of either-ors, and I hear people like say solar is solved now, we should move on to batteries. Well, we can't all do the same thing. We have to solve the energy problem, and we need well beyond a dozen technologies that generate energy, that store energy, that reduce our need for energy by improving efficiency. And I think any technology that has a real legitimate chance of solving more than 10% of that problem, it needs to be pursued, and it needs to be pursued aggressively. And it really disappoints me when one of these promising technologies can't get the funding that it needs to really be explored. And companies like Alta are definitely having a hard time getting what they need to try to scale up that technology. And some very exciting startups are going out of business right now. And for the students here, I would say don't get deterred by this. I'm always asked about Cylindra. The fact that Cylindra failed, it doesn't say anything about any technology that I showed today. I think these technologies can work, and one company's failure doesn't mean that another company with a completely different set of management can't be successment. And I know there are people here who are into finance and policy, and I don't know what's to be done about the investment problem that exists not just for solar, but a lot of renewable energy technologies. But I hope I've convinced you that there are exciting solar technologies in the pipeline, and that people will reopen to the idea of investing in them, because I know there are a lot of students here who have great ideas and would like to start up a company someday, and I hope they'll have that opportunity. And with that, I'd like to thank you all for listening, and I'd be very happy to answer your questions.
Okay, great. We'll take questions, but like always, we'll start with students. So students who've got questions. Oh, the students are all your students, Mike. Okay, please.
I know early in the talk you mentioned a few line of sight ideas that really dealt with manufacturing that were exciting. But were there any more other than maybe the multi-junction ideas and the nanostructured surface that deal more with the performance of the module and increasing efficiency? Anything you consider line of sight?
You're asking about line of sight improvements for like multi-junction cells? Is that what you're asking?
Or anything that deals more with the efficiency rather than the manufacturing?
Yeah, I didn't fully explain that. When a lot of the line of sight improvements for the cost of silicon expressed in dollars per watt is improving the efficiency. More than a third of it is improving efficiency. That is one of the best things you can do, is just get more power for a given amount of silicon and a given amount of glass and a given amount of metal. And you can read Tonio's paper, but a lot of the ideas have to do with improving the doping around the contacts and things like that.
Okay, another one. Yeah, how about that back there?
Hi, yeah, I've heard about progress towards the type of solar paint, and I was just wondering what you knew or thought about that.
So she's asking about solar paint. It sure would be awesome if you could go to the hardware store and buy paint and spray it on your roof. Maybe spray down electrode paint and then high band gap paint and medium band gap paint and low band gap paint and electrode paint. I don't think it's going to happen.
There's a documentary I saw where experts are talking about making progress towards developing a paint, and then you put down the wire and it conducts the electrons. No?
Yeah, I try to strike the right balance between, I've shown technologies today that they're going to be hard to do, but I think we have a chance. I think that's an example of something that I hate to say it's impossible, but these layers need to have very precise thicknesses. If there's a hole and the electrode punches through and touches the other electrode, that kills the whole cell. And I think this can be done in a factory. I believe you can print solar cells on a roll-to-roll coating line, but I'm not too optimistic that you could spray paint. That just do it at home, or that it would be that cheap. I believe you can have cells that you roll out on the roof, which would be very cheap, but not a paint.
Solar wallpaper.
Wallpaper, yeah. I like
right,
wallpaper is more realistic.
Yeah.
Can you speak to the long-term stability of perovskite materials?
Yeah, the perovskites have just been discovered, and my group and others are just starting to look at the stability. And there are definitely issues associated with it. It's a salt, so it dissolves in water. It's certainly not stable in a humid environment, but all that says is that you will have to package the cell. All solar cells, even silicon, are packaged so that the electrodes don't corrode. And I'd say that it's too early to say about just the long-term stability at the relevant operating temperatures and under sunlight.
Okay, more questions. Okay, yeah, how about there? Yeah.
What is your opinion on all the sort of nano fabrication developments that that we see sometimes in papers? Do those have a sort of viable commercial application in the near future, or are they too expensive to make something on that scale, or maybe there's something already?
I think it's hard to answer that question without you telling me a specific technology.
For example, the nanocones that you were talking about, or nanowire solar cells.
Well, putting nanocones on silicon is really changing one processing step on a technology that is already out there. The pyramids work fine, and so unless there's a cost advantage to using the nanocones, there's no reason not to stick to the pyramids, and I'm pretty sure that's what the industry will do in the coming years. If they go to 10 micron thick cells, then I think it's going to be difficult to use the pyramids, and then you may see them switch. And so I think the nanocones may very well be viable there. The nanowires, that's got a lot further to go, and it's tricky to make arrays of wires and to get electrodes on them. One of the dreams there was that you'd sort of grow nanowires and make cells. That actually doesn't work very well. Normally what you do is you make a wafer and you etch away the material you don't want. So you didn't actually get away from having a wafer to begin with. And that's how they got over 13%. So yeah, it's a little further away for the nanowires.
Okay, we'll open it up to everyone and we'll start way back there. Yep.
You mentioned about nanowire, indium phosphide, very low surface recombination velocity. Is it, Professor, effect of if you have any passivating layer, or is just pure the small dimension effect? Because generally I have worked for many years on indium phosphide, and generally indium phosphide and all the 3,5 compound semiconductors have a very large surface recombination due to that there is no native oxide, unlike silicon. So is it any other such phenomena? The physics can change with the dimensions. So is it a nanowire effect, the nanoscale effect, passivating effect, or something else? Could you comment?
I'm really not an expert on 3,5 semiconductors, and I don't know why.
This is amazing.
Yeah.
The SRV, what you have measured,
And I've asked several people who would know more about it than I do, and they said no one knows why the surface recombination velocity is so low. I don't think anyone knew that it was so low until just a couple of years ago.
Okay, more questions? Okay, all right, yeah, we'll take one back there, and then we'll take one here, and that'll be it. Yeah.
The current technology, regular silicon cells, I understand, lose about 1% per year in the sun output. What do you see for the various technologies? Durability, in other words.
Durability? I don't have enough data for, say, silicon and SIGs and CAD-TEL and gallium arsenide. I just don't know. I think 1% per year might be a little bit on the high side for silicon, and the problem tends to be with the electrode, not the silicon itself. And as I think about it a little bit more, it's most likely going to be a product of how good your backsheet is. And I'll do a little plug for DuPont. DuPont would tell you to pay a little extra to get their high quality backsheet, and that if you use that, you probably wouldn't lose 1% per year. So, a good answer to your question might get kind of complicated, and it depends, a lot really on the packaging, more than the semiconductor, itself.
Okay, last question here. Yeah.
Mike, what's the operating temperature of the solar cell that's coupled to a solar concentrator? Do they get very hot?
Well, the temperature of a cell in a concentrator, it's going to depend a lot, of course, on how much concentration you have and how big the concentrator is. If you use a big concentrator, you absolutely have to use active cooling. You're going to need to flow a fluid through there to pull the heat off. And so companies like SolFocus and others talk about using arrays of smaller concentrators so that you don't have quite as much heat, and then it can be passive cooling, which is of course very desirable.
Okay, well, I think we're going to wrap up. Just one thing, we do have a social and a GSEP poster session out there, so join us out there, and thanks, Mike, very much.